So I talked about different types of distance, and so I'm going to use them to build a falloff, basically an intensity transition. So a falloff is a broad term used to mean intensity, and so used, for example, we can see it on reflections many times, where there's a falloff or the reflection amount depending on the facing angle. So for that, there's nodes like Fresnel or Schlick's approximation that basically give us that. And what I'm going to talk here about is more about distance. So of course we can have all sorts of parameters to use to build an intensity map, but here I'm going to focus on distance. And so I have here, if I change a light into spherical, I have access here to the intensity falloff dropdown, where I have linear, inverse distance squared, etc. And so this is the type of falloff that I'm going to talk about. So basically I'm just going to start from the origin. So I have some positions, and their positions are going to be, I'm going to check the length of the vectors of that those positions basically define. And so this is the distance that I'm going to use to build up my falloff and to infer basically an influence map out of it. I'm going to use the auto refresh plugin, the master plugin, that allows me to have the displacement and other node editors to update when I move items. The only drawback is that when I, for example, input some values, sometimes it doesn't update and requires me to basically move some object, some item, so I can see things actually update. Now, why am I using that? Well, the idea is that instead of using Studio Live, I use this because when I have Studio Live on and I turn on VPR, many times the render doesn't settle. And so I want to check here surfacing results at the same time as I move items that are affecting displacement, etc. So I need the render to settle and the displacement to also be take into account the movement of items. So that's why I'm going to use this plugin instead of Studio Live. Okay, so let's go into this object, and into the form tab, displacement node editor, I have the object spot being transformed by the matrix of the item itself. And I'm going to explain later why am I using this instead of, let's say, world spot. I could be using the world spot for that. And then I have that, basically the point positions of the mesh being passed, and they're being passed into several things. So here I split the vector. Here I have the length of the vectors, and here I have the other types of length. So let's look into VPR, what that looks like, because I have this passed into a store material node, which has this material called scalar. And in here I have this get material that I can basically return that value, that material value, and plug it into the diffuse shading. So whatever I do in the displacement node editor is seen in the surface nodes. So let's say that I plug this in here. You can see that now I have basically a linear transition on the x-axis. This is basically what we get when we have here the gradient node and we have the x-coordinate, y-coordinate, z-coordinate. It's basically this fall off here, this type of transition going on in here. And so I can also use the other length. So here's the length as usual, but I can also check the sum, which will give me an octahedron shape. In this case, the slice of that is this shape here, or a cubic shape with the max, etc. So we've looked into that already. Now, what I'm going to look at is how to convert these into something that can control the intensity of an effect. And so usually when we talk about, for example, the fall off around a position, we usually want what's in the center. Let's say I have this position, and what's in the center, we want it to have full force, and what's in the edge, we want it to have none. So it's a transition that goes from 1 to 0, at 1 at the center, 0 at the edge. But what we get here with these is that it starts at 0 and then goes to 1 and then 2, 3, 4, 5. We just can't see it because of everything is white above 1. So what I have is in the surface editor, I have this scalar color, and so this allows me to see the other ranges that go above 1. Right? If I, for example, come into the object displacement node editor and I clamp that value, let's say that I clamp it, I no longer see the values above 1. What I see is this gray, and this gray is the value that is in the gradient is associated with 0. So regardless if it's 0.0 or 1.0 or 2.0, I'm going to see gray. Okay, so I want to have this distance basically inverted in a way. So at the moment it goes from 0 to 1, then 2, 3, 4, etc. And I want it to just be from 1 to 0. And so for that I can use the box step. And the box step, usually the default value is from 0 to 1. And so I'm going to change that to become from 1 to 0. So the black point will be at 1 and the white point will be at 0. And so if I, for example, use this right away in the displacement, so here I have the normal of the mesh and I have some turbulence to give it some, some noise to the displacement. If I plug this here into the displacement to control this displacement, you can see that right away I have the center of the fall off at its full force and the edge at 0. I can also change the radius of this fall off. I can, for example, with the box step, change the begin to 5, and then I have a radius of 5. So the white point will be set at a radius of a length of 5, and the black point is still at 0. But I can also change the black point. I can say I want it to be at 4, and so now I have all these positions here in the middle to have the value of 1. Like I said, 1.0 and 0.0 have the same color in this gradient. So in this case, these values here have the value of 1, while these here have the value of 0. And so basically now I have all these points having the value of 1, and so they all come up, and the transition from that value of 1 is just in here. So it's a thin contour around these polygons. And so I can put this back to 2, or if I put it back to 0, it's going to look like so. Now the reason let's also see now this with the remap node, and I'm going to talk about something else. So I can do the same thing that I've done here with the box tab in the remap node. So I'm going to use the top inputs as I use the remap node. So I'm going to put 5 in here, I'm going to put 0 in here, and you'll see that this will give me the same thing. Right, but the interesting thing is that the remap node also allows me to control the output power. So in here, I'm just displacing the vertices on by 1 unit on the normal direction. But if I put, let's say, 2 in here, now they're being displaced by 2 units, or if I put 3 by 3 units, etc. And the reason that I'm not using the world spot is that if I use the world spot, you'll notice that the fall off coloring is not correct, and you can check that by if I deactivate if I take off the displacement, you see that the colors that they get don't match the ones that they get when they are flat. So that's why I'm using the object spot transformed by the matrix of the item itself, so that I can have an accurate coloring that matches what were the values that they had before the displacement. Right, so this is a nice remap node. Is very nice for this type of thing because allows me to do many things in one node. So I can control the fall off, I can control the output intensity, and I can also control how the transition of the fall off is done. So for example, let me take out the turbulence, and you see that I just get this boring cone. I could, for example, put a function like gain. And so with this, basically, I'm going to control the transition. So I'm going to you can see that now I have this smooth transition from the edge to the center. So I can plug in all sorts of functions in here to control this transition from the center to the edge, which is quite nice. Okay, so let's look into something else. Now let's look into the inverse distance. And I could do the inversion by just doing 1 over the distance. But in this case, what I'm going to do is I'm going to put the distance to the power of -1, which is basically the same thing. But as I change this value here, I also get different things going on. So let's look into that. I'm going to put this into the power function, and I'm going to put -1 in here. And so it looks like this. So the issue with the inversion is that when the values come close to 0, they shoot up really high. And so that's why in the lights, you have the option to have that clamped, especially to, basically to avoid that you have infinite light intensity near the center of the light. But so this looks a bit lighty. If I put here the scalar into the diffuse, you can see this looks like a bit of a light fall off. And so this is how point fall offs work. And I can change this. Let me take off the displacement for now. And you can see that if I put here -2, right? So this really looks like how a light shines. And you see that even though this looks black, it actually never goes to black, right? Because it's the inverse value. So it's approximating black or 0, but it never gets there. And so that's why even though the value is so small, you still see some displacement going on, right? So this is another way to reinterpret the distance. Another way is also to use it as the position on any function. So of course here I used it as a position in the power function. I can use it also as a position on the sine function. So if I plug this in here, if I plug this in here, I get this sort of thing. Let me take off the turbulence, and so you can see that I get this shape. And if I move the object a little bit, you can see how that goes. Right, and of course the cool thing about this is that I can use the other types of distance, so I can use also the sum for this, and this will give me a different output out of the sine function. I can also use the max, that will also give me a different output out of the sine function. And depending, let's say that I also use the inverse distance, so depending on the type of distance that I use in here, I'm also going to get a different output out of that as well. So these are nice ways to reinterpret distance, so that we can create a fall-off and intensity map to basically control effects. Now let's look into something else. I'm gonna put this back in here, put this in here, and put the length, which is a good standard. Okay. We see the color. Let me change this back to okay, and let me put the box step at 1, which is a nice value. So I'm going to reset the position of the mesh, and there we go. So let's look into something else. Basically, let's look into a trick in a way to basically have positions to be considered to be at the origin. So here I have basically a point fall off. So from the origin, there's a radius, but let's say that I want to have a line or a plane or a solid. Well, I can do that by basically playing some tricks. So here I have this sheet of paper, and let's say that I fold it on this direction, but with some limits. And so I fold it really tight, and then I punch a hole where the fold is. When I unfold the paper back again, I get this. So we can also do this in here with by multiplying the values in some directions and have them to be considered to be at the origin where we are going to punch the fall off. So for example, I can multiply the positions, the point positions on one axis. So here I'm going to multiply the positions by 0 on the z-axis. And so what that will produce is that now I have sort of a laser beam fall off going on, because all these positions are considered to be 0 on the Z channel. So they're going to get the value of 1. And so as I move the item, you can see that it's sort of like a projection, laser beam projection that goes on. If I do this on, let's say that's the consideration I have here. If I do this on one axis, I get a line. If I do this on 2, I have a plane. If I do this on 3, I have a box or a solid. And so let me do this on 2 planes. Let's say on this one as well. So now I can see that I have a plane fall off. And if I do this on, all of them, what's going to happen? Well, everything is going to be at the origins. Everything's going to get the value of 1. So, I just basically put all the positions at the origin. So there's not much to look at. But let's look into another approach to this trick. So instead of multiplying, so when I multiply a value by 0, I get it to be at the origin. But I can also do this in another way. I can, instead of multiplying the value by 0, I can subtract the value by itself. So I can do x minus x equals to 0. And I can sort of control if this happens or not by multiplying this value. So let's say that I multiply x by 0, so it becomes x minus 0. Then I get x back again. So by multiplying this by 0 or 1, I can control if this happens or not, if I have the position at the origin or if I have the original position. So, but what I really want to have here is some limits, like I've defined those limits here in this drawing, where I said that it's only going to fold from this position to this position. And so this can be done by clamping this value. I can say I can clamp this value, let's say from -1 to 1. And this means that I'm going to define these two limits, so -1 to 1. So let's look into that. So I have here this little subtree, and so I'm going to pass the position values. And so here I have the subtraction that will perform a similar operation to the multiplying by 0. And here I have the clamp where I define the limits. And here I have the multiply node that defines if that clamping action that goes into the subtract is active or not. So at the moment I have them all active. I'm going to deactivate them all. And I'm going to connect this in here. And I'm going to activate, let's say, the Z-axis. And so now instead of having just a sphere, I have an extrusion of that sphere on the Z-axis. Let me try to show that in a way that can be seen in a 3D. So I'm gonna turn off the displacement for now, and let me just plug this in here to the subtract node. Basically that will perform a delta with my initial positions. And so if I plug this in here, you can see that the mesh kind of shrinked. So what happened to the mesh is that it was folded. And so now what you can see is the hole, the fall off hole being punched in it. And so this is what happens when I unfold the mesh. And this basically might be more obvious if I try to rotate it, and you can see that it actually looks like the the polygons were folded here. And so this is what's happening. Basically the way what I decide in here is the size of the folding. So if I put on the z-axis, if I put 4, now we can see that there's even a bigger folding going on. And so of course, when I then take this out, you can see that actually what I have is a line. And so we can do this on 1 axis or on 3 axes. And so we can define a line, a plane, or a solid. So let's look into that. And so here I define the line. Let me rotate this back, and let's say that now I define a plane by applying it also on the x-axis. And so here the value is 1, here the value is 0, and so now I have a plane. And you can see as I rotate this, you can sort of see the intersection of the mesh with that plane. And so at the center there's a value of 1, but then from that plane to the outside there's a fall off that goes from 1 to 0. And I can use the other shapes as well. I can use the sum, and then you get something like this. I can use the max, and then you get something like this. And I can also use, let's say, the sine function. So for example, I get something funky like this going on. That is basically also using that plane as the center of the fall off. Instead of just a position, now it's sort of a plane. And well, I can also basically do this on all axes, and so I'm going to get a volume. So if I put this on the y-axis as well, now as I move this, let's say to this corner, or if I rotate this, you can sort of see the outline of a cube. Let me put this, let's say, into 2, so they all have the same values. Let me rotate the mesh. So what you see in here, this hexagon is a bit like the slice of a cube. So when we have, let's say, a cube like so, this is the profile of that shape that we are seeing there in the fall off. Okay, so let's look into something else. Let's say that I want to have all this. So at the moment, all we've seen is this happening at the origin. Let me just say that I want to move that away. I'm not going to have a control item that rotates and scales the fall off at the moment. Just going to change the position of it. So I'm going to plug this in here, take this out, and I can plug in the displacement so we can have something nice to look at. And so let's say that I have this control item, fall off control item, this item here, and I wanted the fall off, instead of being at the origin, to be where this control item is. So to do that, what I could use is the distance node. So the distance node gives me the distance between 2 positions, and I could basically put this in here. And instead of using the length that comes from the normalize, I could use this. And so now I have the item controlling the position of that fall off. So that's nice. Whoops. But what I can do, so I have a more complete solution, is instead of using the distance node, what I can do is a position delta, because the distance node will give me the length of that position, of that delta. But I have other distances that I might want to evaluate, not just this one, or maybe I want to evaluate the one axis. And so if I, instead of using this, if I use the delta between the control item and the positions of the vertices, I can use the other solution. So I can, for example, have this just check the gradient on the x-axis, and now I can move my item, and you can see that I'm doing a sweep of these displacement on the x-axis. So that's nice. Now I can have a sweep transition based on the item. I can also have the length, as I've seen before, but I can also have the other types of lengths. I can have the sum, and so I get a different shape, and I can have the max, so I get a different shape, etc. I can also, let's say, put the sign in there, and now it will move where the object moves, where the item moves, right? So this is a nice way to get basically an item controlling that origin. So at the moment we've seen everything from the origin. Now the origin is the item. Let me just do a quick demo of what goes on, for example, with instances. And I'm going to turn off the VPR, and I'm going to activate some instances here. So I have this instancer object. I go inside of it, go into the nodes, and so I have this setup in here. So the base position of the instances, it's their world position, and in order for me to check what's going on, let me just flip the box step. Instead of going from 0 to 1, to go from 1 to 0. And so now I can see my instances, just an array of 15 by 15 cubes. And so 15 by 15 by 15. And so let's see what I can do with these distance fall-offs. So here I have my control item, and I'm doing the delta between the base position of the instances and the control item. Then I'm using the normalized compound, and then if I use the position, I add the position of the control item again. So there's some conjugation going on in here. And in the end, if I want to use the offset output, I have to do a delta between the transformed position and the initial base position. And that's what I'm doing in here. So I'm not going to rotate the instancer or rotate the control item. The instances posing of the instancer item is a bit bugged. I already reported, and maybe hopefully in the future will be solved. So if I plug, let's see what I'm going to do first. Well, first, maybe I'm just going to do the offset. And so as I move the control item, you can see that now the positions of the instances are normalized around the item. So in this case, it's using the sphere normalization. If I put the sum, now I get an octahedron. If I use the max, now I get a cube. And I can, for example, instead of using the offset, I can have this to affect the size of them. So if I plug the length into this box step that is set to go from 1 to 0, I will get them scaled by that fall off based on the position of the control item. But notice that I have this logic node going on in here and going into the weight. The reason for that is that if I'm checking if there is a scale value of 0, and if there is, I'm going to output 0 on the weight. This will make the calculations a bit faster, and you'll notice that if I unplug this becomes a bit slower. This is because even though the instances are scaled to 0, they are still being calculated, and by putting the weight 0 in there on those, it's basically not going to calculate them and make this a bit faster. Now I can also, for example, put this check into the scale, and now I have some sort of voxeling effect where the fall off is basically just either putting the instances up there or not. And so I get this, or if I change the shape of the fall off, now I get an octahedron, some octahedron voxels or a cube voxels, right? Depends on whatever I want to do. But let's say that, well, I can even do the inverse of that. Let's say if I put the invert here, I take this out, let's say like so. Now I have the fall off eating the instances in a way. I can choose another shape. Let's see, like so. I guess I could use the sine function. Let's see what that looks like. It's probably going to do some crazy thing. Well, actually, it's not doing anything at all. Oh, strange. I'd expect to have it do something. But apparently, unless I have to go really far away, yep, it's not doing anything at all. Okay, so what I can also do is combine the two, but because I'm using the inverse, let me try to just use the scale and this and this. Let's see if that helps with the sine. No, it's actually not doing anything. That's kind of strange. I would expect it to do... Ah, there we go. Now it's doing something. Right. Okay, so I can also, for example, put these two in. So the offset and scaling, you get this sort of field that goes on that uses the normalized position as well as the scaling. So it gets cute like this. So there's all sorts of things that you can do in here. I can also do what I've done before with the folding, these folding techniques, where I, for example, let me take off this offset, and where I multiply one axis by 0, and so now I have a laser beam line. Or you can do the one that I did with the clamping, so that you can define a solid. So for example, here it goes from -1 to 1, and it's all the axes are activated. So you'll notice that there's a core of instances with size 1, but then outside that core, there's a fall off that goes from 1 to 0. So you can do that with this, or with, for example, the other shapes. Let's say, in this case, yeah, you can use, in this case, it's using the octahedron fall off. Here's using the cubic fall off, and here's using the spherical fall off. So that's it. I'm going to just show one thing more in here, because I tried to keep this one simple. Let's see that I'm going to turn off the instancer, and I'm going back into this shape, so I have some segue into the next video. And so what I'm going to do is, let me go into the displacement node editor, check what I have in the VPR, and let's say I'm going to put the length in here. Okay, so now I have this fall off that is controlled by this item, and I'm just moving the item. And let's say that I'm going to have this child item of it fall off def to deform the mesh using this deformer. Using this fall off, deforming the mesh using this fall off. And so what I'm going to do, I'm going to copy the vector, transform the vector by an item matrix, and I'm going to put that item in there. So the fall off def. Right, and then after this this subtract node, I'm gonna put this in here, and then I'm gonna put the result onto this position delta. So this delta here is using the initial positions, and so I'm gonna plug this in here, and so this will act as what we've seen in the matrix video, where I had a root and a deformer, and so the root would transform the mesh in an inverse way, and the deformer would transform the mesh in a positive way. So let me reset this. So now as I move the deformer, you can see that everything follows, right? Let's say that I don't want everything to follow. I don't want everything to be transformed, just the fall off area. So what I can do is I can scale this delta by the fall off. And so if I put this in here and I plug this in here, you can see now that, let me turn this off. You can see now that only the fall off points are being transformed by the null. I can also, of course, let's say move this, and so I can change the fall off position, and the child deformer goes along with it. And of course, it's always going to use the fall off defined by the parent. So let me try to select it. It's a bit, oh yeah, I have it locked. So let me scale it up. Let me move it. Let me rotate it. And so this can also act a bit like a wrap, because now I can move this around and it's going to deform the mesh wherever it goes. Right. So in this case, it's a root deformer group pair that is using a specific fall off to affect just a portion of the mesh. I decided to keep things simple here just with the subtract node. But if I wanted a full evaluation, which is what I'm going to look into in the next video, I would just transform the initial positions by the inverse matrix of this item. So I would put this in here, the inverse in here into the fall off, and I would also put the inverse here into the deformer. And so at the moment, everything is the same, but you'll notice that as I scale my parent item, I also change the fall off shape. So now if I scale this, you can see that the fall off gets scaled. If I rotate this, the fall off also gets rotated. And so this is what I'm going to look at in the next video. Things that work now, not just in the axis, but also in oblique directions. Cheers.